Welcome to M1. Today we're looking at dynamics of a particle moving in a straight line, Chapter 4. So first thing we're going to recap here is force diagrams. Force diagram is simply a diagram showing all the forces that are acting on an object. And of course you need to use arrows to label the direction they are acting. And then you need to remember within the question, if it says that they are in equilibrium, it means that all the forces are balanced. So that would mean that the object, if it was at rest, it would stay at rest, or if it was moving, it would continue moving at a constant velocity unless something changes. Here we have a particle with a series of forces acting on this, and what I want to do is first just find my resultant force and then describe the direction or what's happening to the particle. So if I look at this, if I resolve my forces first vertically, so resolving, we just put an R for resolving and an arrow in the direction we go in. And you can see here that we've got 18 newtons and 18 newtons. So 18 newtons going up and 18 newtons going down. Those two are balanced, so no vertical force, because it's an equal and opposite force there. Then let's resolve horizontally. We have 15 newtons in one direction, and then we have 30 newtons in the other direction. Just actually going to write this a little bit differently. So we got 30 newtons minus 15 newtons. So this is going to give me 15 newtons moving to the right. Okay, so resultant force is 15 newtons to the right. And just making a little change there to make this in the same form. Okay, so that's my essentially resolving forces. These are all just vertical and horizontal forces. Nothing too difficult here. Now, as well as these kind of more straightforward forces, sometimes we might have our force as a vector. So imagine we have a series of vector forces acting on a particle. So here I've just done a very quick diagram. Okay, and all my vector forces are made up of I and J. Remember that I is a horizontal of unit 1 and J is my vertical size unit 1. So all I want to do here is resolve both horizontally and vertically. Okay, but essentially that's all about kind of adding my vectors together, adding up all my horizontal components, adding up all my vertical components. So if I look here, and I'll write these in column vector form, so we got 2i, 3j, we got 5i and 0, we got 0 minus 2j, and we have minus 4i minus 1j. So all I've done here is just go around clockwise. So looking at my i's, we got 2 plus 5 is 7, minus 4 is 3, and 3 take away 3 is going to be 0, or 3i here. So in this case, I can say that my resultant force is just 3i newtons, which in this one would just be the same as 3 newtons, as I is just the size of 1. Okay? And equally, I could have a worded problem with vector forces. And I just do the same thing. So I want to first resolve. So that's always going to be my first step here. So I've got 2i plus 1j. I've got 4i minus 2j. And I've got minus 1i minus 3j. Notice that I do tend to use my column vectors just to do these kind of calculations. You don't need to. I just do it because I feel like I make less mistakes if I do it this way. And there we have it. 5i minus 4j. So if you think of this as a rough sketch, it's going to be something like this. 5i 4j will be the positive one. We actually want negative, so ours would look like this. Now we actually want to find this angle and this value of r. So to find r is just simply Pythagoras. So it's going to be the square root of 5 squared plus that negative 4 squared, or just 4 squared would be fine. And that is the square root of 41, or in terms of decimals, let's go 6.4 newtons to 1 decimal place there. Now to find my angle, I want to use trigonometry. So thinking of my angle, opposite, adjacent, so this is going to be tan. So we get tan theta is opposite over adjacent. And what I'm going to use is I'm going to use the positive value of this 4. Okay, just so I can get this positive angle. So this means it is tan theta is equal to 4/5. Therefore, theta is 38.7 degrees. Now this is to 3 significant figures. Now, I should point out with these kinds of questions, they can be a little bit confusing, because in other questions we'll often look at this in terms of a full 360 degrees, you know, other types of questions, but in these vectors, if it's 2i, we just tend to actually find that positive value or for the angle that takes it to I. So, you know, generally you're going to get an answer between 0 and 180. What I would always say is I'd always put my diagram down as well, so I'm clearly showing it, and I can also put in my I here, okay, because then I'm showing my R and I'm showing my angle, and that should make it clear to anyone who is marking my question. A couple of quick questions for you to have a go at here before we start looking at forces and acceleration. Now, if my resultant force isn't zero, it means it's not in equilibrium. So there is a force acting on my object, which means it's going to end up accelerating. And it's going to accelerate in the direction of that resultant force. Now, we also should remember from Newton's second law of motion that F equals ma. So let's look at a few examples now where we bring this into our dynamics of a particle, okay? So where we're looking at these type of questions involving F equals ma. So this example, we have just a straight horizontal motion, which makes it nice and straightforward. We can see it accelerates constant rate. So we know it is starting from, here it is. I knew I'd seen it somewhere. So it's starting from rest. So u equals 0. We get up to a speed of 1 meter per second after a time t equals 2. We want to find a, which is the acceleration. So from our Suvat equations, v equals u plus a t will be the one I want. So we got 1 equals u plus a times 2. So a is going to be a half, or 0.5 if you want it in decimals, meters per second squared. Next, we want to find the tension in the rope. So for that, we need to start by thinking about a diagram. So I've got my little trolley. It weighs 50 kilograms. So I've got that weight acting straight down. Now this is 50 times gravity. Okay, mass of 50, so 50 times 9.8 there, acting straight down. We have a normal reaction, which will act up. We're being pulled in this direction, and then we also have a resistance to motion, which is 20 newtons. And let's call this T for tension. Now, what I want to think about in this kind of case here is using F equals ma. My force is going to be my resultant force. So it's going to be moving in this direction. That's where we are accelerating. So it's t minus 20. T's got to be bigger if it's moving in that direction. My mass is 50, and we know our acceleration is 0.5. So now we've got t minus 20 equals 25. So t equals 45 newtons. So tension in the rope has to be 45 newtons. That's essentially the same as the force that is acting in that direction. Now, it's not always straightforward like a horizontal or a vertical force or motion that we have to think about. Sometimes it is as a vector. So in this case, we can see that r is the vector 6i plus bj. And it's acting at a bearing of 45 degrees. So that's the first thing to think about. Bearings are always measured from north in a clockwise direction. So we know that's the case there. Bearing of 45 degrees. So this is r. And I can think of this vector as being 6i bj. Now, if this is 45 degrees here, then this is also going to be 45 degrees inside this triangle. Okay, and that'll make my life a little bit easier. Now we've got tan 45 is equal to opposite over adjacent. So 6 tan 45 equals b. And since we know tan 45 is 1, b has got to be 6. So therefore my R is 6i plus 6j. And that's my first part done, nice and easy there for A. Now for B, the magnitude, well, the size of R is just going to be 6 squared plus 6 squared, which will be 6 root 2, or as a decimal, 8.5 newtons. We'll do that to 1 decimal place. Now, part C, we want to find the magnitude of the acceleration of the particle. So we know it's going in one direction. We know what F is, because F is my value of R. So that's going to be my 6 root 2. We know the mass is 4 kilograms, and obviously A we are trying to find. So that means that A is 3 root 2 over 2, or as a decimal, 2.12 meter per second squared. I'm just going to do that one to 3 significant figures just to change it up a little bit. It doesn't really make much difference what you choose to do it for these types of questions. And part D, find the total distance travelled by the particle during the first 5 seconds of its motion. So this is now equations of motion. So we got U equals 0 as it starts from rest. We know the acceleration is my 3 root 2 over 2. We know time is 5 seconds. And then S is what we're trying to find, that distance. So that means we need to use S equals UT plus a half AT squared. So with U being 0, that means I got 0 plus a half times 3 root 2 over 2 times 5 squared. That means that as a third, this is 75 root 2 over 4, or better, and so it will be 26.5 meters there. This is 1 decimal place or 3 significant figures, they're both the same. And that's it done, nice and easy. Okay, I'll give you a couple of questions like these two to have a go at, and then we'll move on to the next bit. Looking at connected particles and pulleys. Now, I want to think about, with this kind of example, what forces are acting. So we've got an 800 kilogram mass. That's going to give me 800 G acting down. I've got obviously a cable which is going to have some tension in it, and that's holding the lift. And if I just read a little bit more about the question, we just need to find the acceleration of the lift. So actually for A, we don't need the diagram. So we know it starts at rest. We know it's going to move 5 meters and reach a speed of 3. So that's 3, S equals 5, and we're looking for A. So it has to be V squared equals U squared plus 2AS. So we got 3 squared equals 0 plus 2A times 5. So we got 9 equals 10A. A equals 0.9 meters per second squared. Now, B, the tension in the cable if the lift is moving vertically downward. So for this one, my acceleration is heading downwards. Now, we're using F equals ma, and now if it's heading downwards, 800 G's must be bigger than T. So our mass is still 800 and our acceleration is 0.9. So now all I need to do is rearrange. We'll take the t to the right. So 800 times 9.8. I normally do this in one go, but I'm just taking the extra steps for you guys. So here's my t, and it's 7120 newtons. Now, for part B, we need to think about the the acceleration now moving upwards. So what I'll do is I'll just switch colours here for part B. Part B, now we change this and we want to act upwards. So this time the tension has to be a larger value than the 800G to make it move upwards. We still got a mass of 800 and we still got an acceleration of 0.9. So this time now we've got 800G, which was 7840, plus my 720. Which means that the tension in the cable is 8560. Okay, and it's exactly how you expect it. If you think about it logically, there's got to be more tension in the cable if we're trying to pull that lift up faster than if we were lowering it down. Okay, think about how much effort would be involved if you scale it down, if you were pulling something up or if you were lowering it down. You need more force to pull it up than you would to lower it down. So first thing I want to do here is resolve all my forces. So we've got 5i6j plus 2 and minus 2 and minus 1 and minus 4. So that is 5, 6, 7, 6 along the top, and we get 6. Take away 2, take away 4, so 0 along the bottom. So it's nice and easy. 6i plus 0j, or just 6i. That means it's got a force of 6 newtons acting in a horizontal direction. So that was quite easy. Therefore the magnitude of the force is 6 newtons. So we've got F equals 6 newtons, we've got M we're trying to find, and we've got A, which is 7 from the question. So F equals MA, 6 equals M times 7, M is 6 over 7, or 0.86 kilograms to 2 decimal places there. Now, next thing we're going to look at is connected particles. What's nice about this is you can still consider them separately, but if they are moving exactly the same, as in they're attached to each other, either physically attached as they're touching, or they're attached by like a extendable rod or a taut string or something like that that you can't change, then you can consider them as a single particle. And that makes solving problems like this, as long as you can spot them, very, very easy. So let's jump in with an example. Now, as I say a lot, with these, especially in mechanics, it's really important you start off with a nice diagram. As best you can alter it as you need. It doesn't have to be perfect, but it makes it so much easier. So I've got 2 particles, P and Q. I'm just going to draw them as boxes. It's just for the purpose of my diagram. P is 8 kilograms, so I'm going to put that as 8G, and Q is 2G. And of course they're going to have 2 reactional forces. Now these reactions, these normal reactions, they are going to be different, okay, because the particles weigh different amounts. They are connected by a light inextendable string. So connect them with a string, and then the tensions are going to point towards each other. Okay. Now, it then says it's a smooth plane, so we don't have to worry about that. And we have a horizontal force of magnitude F applied to P in a direction away from Q. So here we go, away from Q would mean that way. And we know that the acceleration, which must probably be acting this way, is 0.4 meters per second squared. So the first thing we want to do is find F. Well, this is really easy. Okay, just F equals ma. We can deal with this as a single particle. That means that F we're trying to find, but the total mass is going to be 10 kilograms, and the acceleration is 0.4 meters per second there. So it's just 10 times 0.4, so 4 newtons. Very easy. Now, part B is the tension in the string. Now for this, I want to be just looking at either P or Q. Now, Q's the easiest one to do, but we'll do it with P first. I'll do it with both of them just to show you. So for P, we'd be looking at F equals ma. We're moving to the left, so we've got F, which is 4 minus T, the resultant force there, moving to the left. The mass is 8 and the acceleration is 0.4. So take T to the right and we get 4 minus 3.2, which is 0.8 there, or T equals 0.8 newtons. And if I did it with Q, which I did say was the easier one, we've only got one force acting on it, which is T. So F equals ma is just T, and their mass is 2, and my acceleration is 0.4. So you can see there that T is 0.8. So using Q is much better because we don't have to use this value of F that we found, which means that it's a much safer option to take in an exam, and it's also quicker and easier. Now the final part, I'm not going to write this down, I'm just going to talk you through it. We're talking about the string that is light and inextendable. So if this is inextendable, it means that it's going to stay the same, so it means it's what allows us to treat these as a single particle, because this is not going to stretch in any way. So it means that these two will accelerate exactly the same. Now, with it being light means we don't have to worry about the mass of this string coming into consideration. Okay, it will also mean that this tension is going to be even throughout. So tension's exactly the same because it'll be the same tension right throughout the entire length of the string. And that's part C done. So just kind of putting that into words. So again, let's get a quick little sketch in here. So this is going to be my lift with my tension in my cable, and then we've got box A and box B. Box A rests on top of box B. So this is box B and this one is box A. A is 110 and B is 190. Also the lift has mass of 1,700. We've got the lift is supported by light in extendable cable and is descending with constant acceleration of 1.8 meters per second squared. So part A is relatively easy. We're just looking at F equals ma. The force is going to be a downward force initially, so we got 1700 plus 110 plus 190 minus the tension. Sorry, and I should put a G in there, almost forgot that G. Okay, let me just tidy this up a bit. Minus the tension equals, and the same value for my mass times by my 1.8. So we got 2000 G minus T equals 2000 times 1.8. So T here is 16,000. Let's turn that around, 16,000 newtons. Now for this one, the force exerted by box B on box A is going to be the same as the force exerted by box A on box B. So if I think of box A, it's going to have a normal reaction R. Going down is going to be my 110 G. So if I think of F equals MA, we know we're moving in a downward motion, so it should be 110 G minus R equals 110 times 1.8. And it's also obvious because if R was bigger, this would actually start to move upwards, which wouldn't make any sense. So now we've got 110 G minus 110 times that 1.8, and that is my value of R. So R is 880 newtons. Incidentally, these two being the same, you could have factorized them out very much the same as part A with the 2000. Now, part 2 is a little bit harder, but only very slightly. So, I think there's more than one way of doing this, but we could consider box B. And again, you know, we've got this 190G acting down, and let me just call that first one R1, so I can call this one R2. R1's in there. And we can look at this in very much the same way. So in this case, we'd actually have 190G minus R2 equals this 110 times not 110. I'm exactly copying the one above there. 190 times 1.8. However, there is also an additional force on that, isn't it? The one from the first part, the 880 newtons. So that's also acting down on, you know, from B down onto the lift floor, if that makes sense. Yeah, so you've got the same as this, the box acting down, plus, so it's this one. So this one, exactly the same way as we worked this one out, the reaction from this box down, but then we've also got this force from above as well. So that should, with a bit of rearranging, mean that I have 2,400 newtons. So this is, you know, my 880 plus my 190 times 9.8 minus this, as I've taken out this side, and that is then my final answer. Alternatively, you could consider the force of B acting down on the lift, give that a letter. So, you know, that would be S maybe, ST, up to you, could be anything, but you just want to kind of state it. Then if we think of what's involved, our overall forces are going to be 1700 G plus S, as that's also acting downwards, minus T, that tension that is acting upwards. My mass is 1700 and my acceleration is 1.8. Now T is obviously 16,000, so we've got S plus 1700G minus 16,000 equals 1,700 times my 1.8. So, and we get the same answer there. Okay, so it doesn't make a difference in which way you do it. You just need to think of which way is easier for you. One object, because they have an equal and opposite reaction, it doesn't matter which way round you think of it. Think of either the box acting on the lift or the lift acting on the box. It's totally up to you. Now for this question we have a car of mass 900 kilograms and it is pulling a trailer of mass 300 kilograms. So along a straight horizontal road, tow bar is parallel to that road, so we got our tensions there. Normal reactions, let's call them R1 and R2, and obviously our weight, which is our 900 and 300 times G. There is, and I'm going to use a different colour with this, there is a force of 200 newtons this way and a force of 100 newtons that way, and this is the direction that we are accelerating or we are moving. Now the engine produces a constant horizontal drive force of 1,200 newtons. So now I put all my forces on the diagram and I can use that for all the parts. So let's start with part A. We need to show what the acceleration is. So F equals ma. So total force. So we've got 1,200 pulling it forwards, but we're losing against that 200 and 100 from the resistances. My total mass is 900 and 300, so it's 1,200 kilograms, and A we are trying to find. So this gives me 900 equals 1,200A. So A is 900 over 1,200. I'll put that down, which is obviously 3/4, which is our 0.75, as we required. Now to find the tension in the tow bar, we have to consider these separately. We can pick either one. It's probably easier to go with the trailer. Certainly looks a little bit easier. So it's F equals ma. We're going to have a forward motion in this direction. So that means that T is going to be bigger than the resistance. So T minus 100 newtons is 300 kilograms times A. And A, of course, is 0.75 from the first bit. So T is 325 newtons. Of course, you could have done it with the car instead. So if you did it with the car, you would have had 1,200 minus T. And actually, almost forgot there, also need to minus 200 newtons for this resistance here. So the T and the 200 is going to the left, 1,200 is going to the right. And then M is 900, and we got 0.75. So you can see here we would have T, if I take T to the left, and then take T to the right, and then on the left we got 1,000 minus 900 times 0.75, and that gives me my 325 newtons. But what you can see is the reason well, slightly less working out to do the trailer, but the main reason that the trailer is easier is that T is positive, because that is the driving force there for the trailer. Whereas with the car, T is negative. That means I have to do a little bit more rearranging, and I open myself up to a potential making a silly mistake. So that's why I go for what I would say is the easier option, is the one where the value I'm trying to find is positive rather than negative. Now, this driver sees a red light, takes his foot off the accelerator. So we've now no longer got an engine producing any forward thrust, and applies the brake. So if he applies the brake, then we've basically got an F going in this direction. Okay, given the resistances to motion stay the same and the magnitude of thrust in the tow bar is 100 newtons, find the value of F. Now it's this type of question that is, well, this part of the question, which is where it gets a little bit harder. So let's look at the trailer. So first thing we can say now is that we've got a new value of acceleration because we're decelerating. Okay, so if you're decelerating, you might want to consider now which side it is positive or which direction. It makes sense to put it to the left because we are decelerating. Now, if I think about the trailer, and I'm essentially going to be using F equals ma, we know the mass is 300, and we don't know the acceleration. We're trying to find that. Now, let's look at the force that's acting on the trailer. So here we've got 100 newtons, and that's the resistance to motion. So we've got 100. And then it's very tempting to look at this T here, which is in the tow bar. But what we actually have to do is think about all the forces that are acting on the trailer. So there's also, a force of 100 newtons, which we're told in here, which is also acting on the trailer. So there is actually a force of 200 newtons acting on the left. And a good way of thinking about this is that if you were actually taking the 100 newtons that's going to the right, then this would actually not be decelerating. It would be going at it'd be an equilibrium. So that obviously isn't what the question's telling you. So it makes sense then when you're thinking about it. So it's all the forces that are acting on this trailer. So here we've got 200 equals 300A. So A is going to be 2/3 meters per second squared there. Now that we've used the trailer to help us get the acceleration, we can now think of the car. So again, we're thinking of F equals ma, and we know the mass is 900, and we know that the acceleration or deceleration is 2/3. What we need to do is work out the forces that are acting on the car. So thinking about what's trying to essentially slow it down is our F and our 200. Okay, these forces are acting on the car. But also, this from the tow bar now is acting this way. The thrust is pushing against the car. So it's 100 newtons against the car. So much like in the trailer, we used the 100 newtons and essentially the arrow going to the left for acting on the trailer. We're using the F and the 200, which is going left, and this thrust here, which is going right, which is acting on the car. Now simplifying this, we get F equals and 2/3 of 900 is 600, plus, and then 200 minus 100 was 100, wasn't it? So sorry, it's not plus, it's minus 100. So F equals 500 newtons. So the braking force is equal to 500 newtons. Now, just before I go any further, one more thing to kind of note is that I've seen these questions before with an additional part where it talks about these resistances and talks about comparing it to, you know, real life or the model and what's wrong with the model or what might change. And, you know, essentially it would be these resistances. The resistances to motion, which is in this case 100 and 200 newtons, they are going to change, aren't they, in real life? You know, as this vehicle slows down, those resistances would change. They have to change, because otherwise, when you're braking and you only apply the brake, once you stopped, if these didn't change, you'd start going backwards, which would make zero sense. So, you know, these resistances, which are probably due to friction or air resistance, combination of the two, these resistances have to change in real life. Okay, so if you get a part of a question which does talk about these resistances, just, you need to think of common sense. Think the problem through, think common sense, and you should be able to get that kind of thing across then. Now, the final part in this chapter is about pulleys. One thing about pulleys is that you cannot model this as a single particle, because although they are connected, they would actually be moving in different directions, and that whole definition about a single particle is that they're effectively attached or moving in exactly the same direction at exactly the same speed or acceleration, exactly the same time. Okay, which is how you can model them as a single particle. So it doesn't work for pulleys. Now, most of the pulleys we deal with is a smooth pulley, so no resistance, a light inextendable string, so you don't have to worry about the weight of the string or whether it would stretch and so on. That means that the tension is going to be even throughout. Okay, so these things will all help us be able to solve these problems easier. So let's get stuck in with an example. So first things first, we want to do a very quick little sketch here. So we've got a pulley, we've got two masses on it. This one's going to be km and one is going to be 3m, P and Q. And then I've got to think about tensions in my string, and these will both act in both directions as so. And then we know that Q is going to descend with acceleration, which is 1/3 g. So first step is calculate the tension in the string as Q descends. So for Q, that's what we're looking at. F equals ma. The force is going to be 3m, it's got to be going down, multiplied by g for that weight. Should put the g in there really. Minus T for the tension. So my overall force is going down, so this minus this. The mass is going to be 3m, and the acceleration is 1/3 g. Okay, hopefully not too difficult so far. So T is going to be 3mg minus mg. So T equals 2mg. And of course this is newtons. Part B, show that K equals 1.5. So let's look at what's happening at P there. So F equals ma. This time it's moving upwards. If Q's moving down, T's obviously moving upwards. Sorry, P's moving upwards. So T is going to be larger than K. And then the mass is Km times by our 1/3 G for acceleration. So T equals Kmg plus 1/3 Kmg. So this is going to be 4/3 Kmg for T. Now, we already know from over here what T is. T is 2mg. So let's substitute that in, and we get 2mg equals 4/3 Kmg. M's will cancel, G's will cancel. Multiply by 3, divide by 4. So it's 6/4. So K is equal to 3/2 or 1.5 as required. Now for part C, I'm not going to write this down, I'm just going to state it. So state how you have used the information that the pulley is smooth. Well, if the pulley is smooth, then there is no friction. So the magnitude of acceleration of P is the same as the magnitude of acceleration of Q. Okay, so it just means that these are accelerating at the same speed as there is no friction in the pulley. Now, question continues. After descending for 1.8 seconds, particle P reaches the plane. It is immediately brought to a halt by the impact of the plane. The initial distance between P and the pulley is such that the subsequent motion P does not reach the pulley. So that's quite a standard thing. So what you're thinking is Q is moving downwards until it hits the bottom. So Q is now going to be, all the way down here. It's moved in this direction, while P has now moved in this direction. Okay, now as Q has dropped down, it's hit the floor, but P has not hit the pulley. Okay, that's important because what that means is if it hit the pulley, then this probably wouldn't have hit the floor. Or if it hits the pulley at the same time, then this would stop. But because it hasn't hit the pulley, once this hits the floor, it's no longer pulling P up, which means that then P is moving freely under gravity. And that's then how I can model it. Okay, moving freely under gravity. Now, my first step here is going to be to see how far Q has travelled in this 1.8 seconds, because that'll give us this height here, which we'll call S. So we're going to find this height S, 1.8 seconds. Maybe we'll call it S1 in case we need another height. We know that the acceleration is 1/3 G. What else do we know? We know it started at rest. We can't say it finished at rest because it did come to an abrupt halt. Sorry, I don't know why I wrote 1.8 in there. That's what we're trying to find. T is 1.8, isn't it? So we're looking at S equals UT plus 1/2 AT squared. So it's going to be 0 plus 1/2 times 1/3 G times 1.8 squared. And this gives me 27/50 G. I'm leaving it in terms of G as this overall here is in terms of G. Okay, and just as a decimal, this is obviously 0.54 G, which might be a little bit easier to think of. So we've worked out that initial distance. Now at this point, P is moving freely under gravity. Okay, so if we think of now for P, and this is moving freely, we're going to be thinking that while it's moving up, it's going to have an initial speed. We don't know that, but we can find it. We know the acceleration is going to be gravity probably minus g if I'm thinking of it down. We don't know t, and we don't know s. So there's, we know v. V is going to be 0. So we know 2, we can work out u, okay, because we can work out what v is when this part hit the surface, because the moment it hit the surface, that's the start of p's speed, its velocity. So let's do that. Let's change the color up. So we want to find v, and we know a is 1/3 g, u was 0, and t was 1.8. So we got v equals u plus at, 0 plus 1/3 g times 1.8. And that is 0.6 g. So that will be our u over here. So 0.6 g. Now we don't need t, we want s, don't we? So we've got v, u, a, and s. So v squared equals u squared plus 2as. So it's 0.6 g squared. Oh, sorry, no. V is going to be 0, isn't it? U is 0.6 g squared plus 2 times my minus g times s, which is what we're trying to find. So we've got 2gs equals 0.36 g squared. So s is 0.18 g. Now I've got all the information that I need. And now all I have to do is think of it logically. So if q moved this distance of s1 here, and let's call the other distance my s2. So if q moved s1, then p would have moved s1 up. Okay, so if q's moved down, s1 down, which is the 0.54 g, p is moved at 0.54 g up. And then it's carried on up another 0.18. So its total height above the horizontal plane will be this distance plus another one plus the 0.18. So just to kind of illustrate original starting position, q dropped down, so p went up here, the same distance as q dropped down, and then freely under gravity it went up to here. So in total it's the 0.18 plus 1 0.54 g and another 0.54 g. So the total height above surface, which is the important bit, is 2 times 0.54 g plus 0.18 g, which is equal to my 1.26 g. And it's all about that height above the surface. Okay, p itself has travelled these two distances from here to here, but it has this additional height above the surface. So from the question, we can see that acceleration is in this direction. Okay, it's for A is heading down or B is heading up. And we've got to think about our tensions in the string as well. Now for part A, we know that U equals 0. We know that the time equals 1.25 seconds, and we know that the distance is 2.5 meters, and the acceleration is something we want to find. So we need s equals ut plus a half AT squared. And all I need to do is obviously substitute in and then rearrange. And that's A done. Now, B, we need to find the tension in the string as A descends. So I missed out part of this question just about the smooth pulley and so on, just because it was too big to write it all down. But the tension of the string is going to be the same on both sides. So I'm thinking of F equals MA and considering B, because what happens to B is also going to happen to A. So B is T minus 3G, 3 times the gravity, yeah, the weight of the ball B. The mass is 3 and the acceleration is 3.2. So nice and easy, just add 3G to 3 times 3.2. And T is 39 newtons. Now we know the tension in the string, we can work out what the mass of A is just by looking at A. So we know it's mg minus T, so this is for our F equals MA. And then we've got M times 3.2. Now we know T is 39. So mg minus 39 equals 3.2 m. So mg minus 3.2 m equals 39. Factorize out the m, so g minus 3.2, or you can actually just work that out because g is 9.8. So this is the same as 6.6 m, and that's 39. And then dividing by the 6.6, we get 39 over 6.6, which is 65 over 11. As required. So for this one, we've got to imagine now that A has hit the ground, and B now is flying up this way, moving freely under gravity. So what we've done is that this A is now all the way down here, and that B will be up here somewhere, flying up freely under gravity. Now, from the moment it starts flying freely, that is when the string is going to be loose, as it says. Okay. It's going to reach a point where its velocity is 0, and then it's going to drop back down. Okay, so the time taken to get up to that point is going to be equal to the time taken to get back down, where it will then make the string taut again as it hits there. So we want the time in one direction and then doubled to get our final answer. So U, we can find V would be 0, T we're trying to find, A will be our gravity because we're moving under gravity. So let's find U first. So the speed that this one starts moving at is going to be the same speed or same velocity as when A, the moment A hits this ground. So this is what we had earlier to find A. This time we're going to use it to find V. So we want to use S equals U plus V over 2 times T. So it's just a matter of substituting in everything that I know and then rearranging. Now that I've got that V becomes my U for my other particle B. So now we've got U, V, A, and T. So V equals U plus AT. So we have 4. sorry, wrong way around then. 0 equals 4 plus minus g times t. So gt equals 4. Obviously g is 9.8. So 4 divided by 9.8 is 0.408 seconds. And as we said, we need to multiply this by 2, therefore total time equals 2 times my 0.408, which is, in my calculator I get 40 over 49 seconds, or 0.816 seconds to 3 significant figures. So you can leave it as a fraction or as a decimal here. Now this question, we can see it's on a rough horizontal table, so there is going to be friction involved. Okay, it's attached to one end of a light inextendable string. The string passes over a smooth pulley fixed at P. The other end of the string hangs freely, blah blah blah. Now the resistance to motion of A from the rough table has constant magnitude F. So this is going to be my F. The system is released from rest with the string taut. That's nice. We can put our little tensions in here. They should all be the same because we got light inextendable string, we got smooth pulley. There should be no issues there. Now I'm just going to get rid of some of the information we don't need anymore, just to make a bit more room. Now for A, we know that B is going to descend a distance of 0.4 meters in a time of 0.5 seconds. We know it started from rest, and we want to find the acceleration. So S equals ut plus a half at squared. Again, then just simply substituting everything in and then rearranging. And we will get that A is 3.2 meters per second squared. Next, we want to find the tension in the string. Just before I do that, you should always, it's nice to kind of finish the question off with a sentence. Like so. I don't always do it in some of these videos, but it is important to kind of state your final answer just to make it very clear. Okay, it shouldn't really affect your, exam questions, but it is best to make things clear. Now, part B, as we were saying, we need to use F equals ma. The mass is obviously heavier because this is heading downwards. So we've got our 0.8 G for the weight minus the tension is equal to 0.8 times the 3.2 that we just found. So all I need to do now is rearrange for T. And we should get 5.28 newtons there. Now that we've found T, we can find C. So for T, we were using B. In part C now, we're going to use A, that block of wood. So it's moving to the right. So T is going to be larger than this F. So we'd have T minus F is equal to my mass, which is 0.5 times my acceleration. Okay, so F equals ma. Now obviously we know what T is. T is 5.28. So all we need to do then is rearrange for F. So F equals 3.68 newtons. Now before we go further on to D, just to bring your attention to one thing here. We're using that G is equal to 9.8. Okay, so really we should be putting these answers to that one decimal place or the two significant figures as well, as that's what the gravity we're using is. Often it is acceptable to do that extra decimal place like I've done here with the 2 decimal places, but in practice you should use the same or less decimal places or the same or less significant figures, okay, just to show the accuracy. If this is rounded to 1 decimal place, really this is going to be accurate to 1 decimal place or less. Okay, so it's just a little point. It shouldn't affect you in your exam, unless it did say to a suitable degree of accuracy, but it's just to kind of make you aware there. Now it says state how in your calculations you've used the information that the string is inextendable. So if it's inextendable, then it means the acceleration of B is equal to the acceleration of A. And that is what we've done, okay? So if there's no stretch, then this acceleration is equal to this acceleration. So that's what you have to just say there for part D. Final question of this video. So we go a car of mass 1.25 tons tows a caravan of mass 0.75 tons. It's along a straight road, so total resistance to motion, so that'll be over both of the vehicles, is 1200. Accelerates from rest to 25 in 20 seconds. So first let's kind of put this as a little diagram. So here we have roughly kind of all the information that I've given initially. Now I've just stuck the 1200 newtons at the end, but essentially I'm going to model these as a single particle here. So something like this. Okay, this is what makes sense. Now I'm going to use my equations of motion to find A. So you can see here we've got U, V, T and A. So V equals U plus AT. 25 equals 0 plus 20 lots of A. So A is 25 over 20, which is 5 over 4 or 1.25 meters per second squared. Now I think of my F equals MA. Bit annoying I used F again here, but F minus the 1200 equals 2000 times by my value of A. Incidentally, I did change these from tons into kilograms just to make it easier. Remember, there's 1,000 kilograms in a metric ton. And back to this, I just need to rearrange for F now. And we get 3,700 newtons. And that's part A done. Now, before we go further, now it tells us that the resistances to motion experienced by both the caravan and car are in the same proportion as their masses. So what I can do is I can change this now into its individual resistances. So what I'm going to do here is set these up as a ratio first. And this is going to be in the ratio of 3 to 5. Okay, which is a total of 8. I've got that 1200 divided by 8, and that's 150. So 3 times 150 and 5 times 150 there. So we have 450 newtons and 750 newtons. So that's now splitting my 1200 up into its individual resistances. So redrawing my diagram, I have my 2 separate vehicles, my 1250 kilograms and 750 kilograms for the car and the caravan. Caravan now has a resistance force of 450, the car is 750, and of course we have the tension there. We know this is 3,700 newtons, and we kind of have two separate normal reactions there, but we don't worry so much about those. Next, I want to find the tension in the tow bar. So it makes sense to look at the caravan. This is the easiest one to do, as then I've got T is the larger value. Okay, T minus the 450. So it just makes my calculation a little bit easier. So and this is now part B, isn't it? For the caravan, we're going to look at, so F equals MA. So T minus the 450 is the force driving it forwards. 750 is the mass, and the acceleration is 1.25 that we've already calculated. And then we have that this is 1387.5 newtons. And of course, you did it with a car, you would get the same answer. It's just the calculations easier for the caravan. Now, for part C and D, we can see that the car and caravan have been travelling steady at 25 meters per second, and the tow bar snaps. Assume the caravan experiences the same resistances as before. Calculate the distance until the caravan comes to rest. So if you think about it, we've now just got the caravan, so it's got no force pointing forwards. We've got our 450 newtons, it's 750 kilograms, and that's kind of it. We know that its current speed was 25 meters per second. We want to try and find the distance, but we don't know, and we will know V equals 0, and that's about all we do know from this initially. Okay, but we can find the acceleration because we can use F equals ma. Now, while we are decelerating, I'm going to take this as my positive direction because that's the distance we're still going to be moving. So my force is going to be minus 450. We're going to get 750A. So A is going to be minus 0.6 meters per second squared. Okay, so I can fill my value of A in now as minus 0.6. If you didn't use that as the direction, you'd have a positive value for A, and then you'd end up with a negative value for your distance, but you can still talk that through. So we got U, V, A, and we want to find S. So V squared equals U squared plus 2AS. So that's 0.25 squared plus 2 times minus 0.6 times S. So it's 1.2S equals my 25 squared. So S equals 520.8 meters. And that is then part C done. Part D, give a reason why answer to C may be unrealistic. Well, there's lots of reasons you can give here. You can go with the fact that the resistances are unlikely to remain exactly the same. It's not going to stay as 450 for the whole way down. You can say as a caravan, it's unlikely to go in a straight line. You can also, if you think of a caravan, they generally have those kind of two wheels and they attach at the front. So if that breaks, the front of the caravan is just going to drop straight to the floor and dig into the floor. So that would actually create a much bigger resistance, and it'll probably stop a lot shorter. So you kind of want to give a reason like that and just say that the distance is likely to be less than what you calculated in C. Hopefully you found some use with this video today, and if you did, don't forget, comment in the comment section, anything you're unsure about, or if you want to ask a question, or if you spot a mistake that I might have made. And also, if you haven't subscribed, please consider hitting that subscribe button. You know, it helps me out and helps you find these videos if you need anything in the future.